Hello, today I'll explain how to draw a most stable chair conformation of, let's say, any cyclohexane that's given to you, because this is a frequent problem and let's solve it right now. So in order to actually, let's say, transition these wedge bonds onto this cyclohexane, let's say, chair conformation, we can basically do it from anywhere. We can start from here, here, basically any carbon. So let's say I would just for simplicity, I would start from this carbon. So the first carbon right here has a wedge bond up, so that means our bond, the carbon, should be going up. So like this. Then another one's up. Again, we put it up on this one. And then lastly, we have another up, so we put it up on this one. So like that's pretty simple, but this is not the most stable one. Because in order to get the most stable chair conformation, we need to get as many as possible of these carbons in the equatorial position. So here we only have one right here, it's in the equatorial, the other two are in the axial. So in order to actually get the most in the equatorial position, we have to realize this, that these two are gonna be in the same position no matter where we put them relatively to each other. So if this one's equatorial, this one's also always going to be equatorial, facing up. And if this one's axial facing up, then this one's always going to be axial facing up. But this one is different from these two right here. So while this one's going to be always, let's say while this one's equatorial, these are going to be axial. And while this one's going to be axial, these two are going to be equatorial. That's just how it is. So in order to get the most equatorial, because that's the most stable, we would want these two to be equatorial instead of this single one, because two is more than one. So what we do, we put this one equatorial up, so we have to preserve the up configuration. So let's see, we can start anywhere again. So we can literally start, let's say right here, right here. So this one, we can put it right here as up, but let's say equatorial. Then we're going this way, so clockwise. So we can see this one's going to be up again, but now it's going to be axial. And then we see this one, so we're continuing clockwise. So this one's going to be up, but now it's going to be equatorial. So this is the most stable chair configuration because it's got one equatorial and then it's got another equatorial and then it has one axial. Unlike this one where it has two axials, this one only has one axial. So this is clearly the most stable chair conformation. We could draw it any way. It's actually pretty cool here because we could, let's say we make this chair conformation and we could literally just start, let's say from here, because we want the first one to be equatorial. Since it's going to face up equatorial, let's just put it here, because if we put it here, it's going to be axial. So let's put it here. Then the next one, it's also up, so we're putting it like this. And then again, we're putting it like this. So again, this and this are basically the same. These two are exactly the same. If we were to draw a cyclohexane, just a regular 2D one with these wedge bonds, these two would yield the same image. It's just that we can literally start from anywhere. And as long as these two are equatorial, that means it's the most stable configuration because we have to get the most in the equatorial position. Alright, so let's continue. I'll continue solving these problems and hopefully the message becomes pretty clear. So here we have another problem with all of these bonds facing upwards. And this is how we can solve it here. It's different from the previous problem. So again, we'll just simply put them on the chair conformation. So we can start from any of these carbons. We'll just start from this one first. So here it's up. So since it's on an up carbon, we'll make it axially up. Oops. Then we will continue. Skip a carbon. So we're skipping one right here. So we're going to skip one right here and put one up right here. And then lastly, we're going to skip another carbon. So we're going to skip one right here and put one up right here. So notice all of these are going to behave the same because all of them, in this case, are going to be axially up. So if they're going to be equatorial, if we switch into equatorial, they're all going to be equatorial also. So let's say we take this one and we put it in an equatorial up position, so we need to find a carbon that will allow us, so either this one or this one or this one, either one, we can make it go equatorially up. So let's just take this one right here. So we can make it equatorially up right here. Then we skip. So again, equatorially up. And then we skip another one. And here we see it's up, so it's equatorially up right here. So this is the most stable chair conformation, because all I did was that I noticed that these three behave exactly the same in terms of if this one's going to be axially up, then all of these are going to be axially up. If this one's going to be equatorially up, then all of these are going to be equatorially up. And in order to obtain the most stable conformation, we need them to be all equatorial. So we only have to put one in an equatorial position on any carbon. So I chose this one right here. So this one's equatorially up. And then we just translate this diagram to here. So this one's up, so we see it up right here. Then we skip one right here. So we skip from this one right here. So this one's up. So in this case, since it's a down carbon, this one's going to be equatorially up. And then we're going to skip one right here. And again, it's going to be equatorially up right here. So that's how you basically solve these problems. And it's if you want to get more information on visualizing these cyclohexane chair conformations, then watch my previous video and hopefully you'll help too.